S12. So today I will present to you about parallel resonance circuit. First, the introduction. RLC circuit consists of three elements: resistor, inductor, and capacitor. Capacitor will produce a parallel resonance, also called anti-resonance, circuit when the resultant current through the parallel combination is in phase with the supply voltage. At resonance, there will be a large circulating current between the inductor and the capacitor due to the energy of the oscillation. Then parallel circuit produce current resonance. A parallel resonance circuit stores the circuit energy in the magnetic field of the inductor and the electric field of the capacitor. This energy is constantly being transferred back and forth between the inductor and the capacitor, which result in zero current and energy being drawn from the supply. This is because the corresponding instantaneous value of IL and IC will always be equal and opposite. Calculate parallel resonance circuit. There are two methods can be used. Calculate the branch separately and add them. Second, calculate the admittance of each branch to find the total current. Impedance. If the parallel circuit impedance is at its maximum at the resonance, then consequently, the circuit admittance must be at its minimum, and one of the characteristics of a parallel resonance circuit is the admittance is very low, limiting the circuit current. This is the waveform of the impedance. Impedance. The circuit current is constant for any value of impedance. The voltage across a parallel resonance circuit will have the same shape as the total impedance for a parallel circuit. The voltage waveform is generally taken from across the capacitor. Frequency resonance. The admittance of the circuit is at its minimum and is equal to the conductance. G is given by 1 over R because in a parallel resonance circuit, the imaginary part of the admittance. Susceptance at the resonance. The inductive susceptance BL is inversely proportional to the frequency as represented by a hyperbolic curve. The capacitive susceptance BC is directly proportional to the frequency and is therefore represented by a straight line. The final curve shows the plot of total susceptance of the parallel resonance circuit versus the frequency, and is the difference between the two susceptance. Alright, as we can see, on the left side, this is the inductive susceptance, which have produced hyperbolic curve. In the middle, this is a capacitive susceptance, which produces a straight line. Below the resonance circuit frequency point, the inductive susceptance dominates the circuit, producing a lagging power factor, whereas above the resonance frequency point, the capacitive susceptance dominates, produce a leading power factor. The resonance frequency Fr, the current drawn from the supply must be in phase with the applied voltage as effectively there is only the resistance present in the parallel circuit, so the power factor becomes 1 or unity. Theta is equal to 0. The impedance of a parallel circuit at resonance is equivalent to the value of the resistance and the value must therefore represent the maximum dynamic impedance. To calculate impedance, Z is equal to L over R times C. Current in parallel resonance circuit. Resonance is the current flowing through the circuit must be also at its minimum as the inductive and capacitive branch currents are equal. I equal to LC, IL equal to IC, and are 180 degrees out of phase. The calculation is shown. So that's all from me. Thank you.
Okay, I want to talk about the bandwidth and selectivity. This is the graph for the bandwidth. Next, the bandwidth of a parallel resonance circuit is defined in exactly the same way as the series resonant circuit. The upper and the lower cut-off frequency given as frequency upper and frequency lower respectively denote the half power frequency, where the power dissipated in the circuit is half of the full power dissipated at the resonant frequency 0.5 in bracket I power 2 R, which give us the same 3 dB point at a current value that is equal to 70.7% of its maximum resonant value. If the resonant frequency remains constant, an increase in the quality factor Q will cause a decrease in the bandwidth. This is formula. Next, the selectivity or Q factor for the parallel resonance circuit is generally defined as the ratio of the circulating branch current to the supply current. This is the formula as you can see. Next. Okay, that's all. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad Taufik bin Kamru Zaman. So I will continue the presentation. Now I will show you the simulation. The simulation is using multi-sim software. So as you can see from the simulation, this is the parallel RLC circuit. Uh, so we're going to find out whether the circuit is in resonant state. So for this circuit, I will be using VRMS as V input, voltage input, and the resistant, the inductant, and the capacitance. I'm using 4 multimeter to collect reading current in each branch. So this is the I total, the IR1, the IL1, and IC1. So the multimeter is connected in series. So that show I'm going to measure the current. So as you can see, the input is in 100 volt VRMS and the frequency is 10 Hz. So now I will run the simulation. Click the all multimeter. This is the I total, the IR1, the IL1, the IC1. So according to the theory, in resonance state, the current for L1 and C1 should be same, which is IL1 equal to IC1. So as you can see, this is not same current value. So we're going to find out which frequency will make the circuit is resonance state. So we will use different value of frequency. So I have shown the frequency from the calculation that Zaim has done. The resonance for the circuit should be in 32.5 Hz. So we'll see whether the frequency is in resonance state. So we put here is 32.5. So we're gonna run the simulation. So as you can see, the IL1 and the IC1 exactly the same, but this is the same value, the highest value that I can get, the same one for the IL1, the IC1, which is 2.5 in the calculation. So from this current value, it shows that the current is in resonance state when the frequency is 32.5 Hz. So from this circuit, I have run many different values for frequency. So I'm going to show you the result data. So this is the result that I've been simulate using different value of frequency, which is 10 Hz, 32.5, 50 Hz, and 100 Hz. So only the frequency on the 32.5, the IL1, the IC1 has almost equal value, and the other frequency is not. So that's all for the simulation. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zain and I will come from the UI 162. Okay, I will present the calculation for parallel resonance. Okay, for parallel resonance circuit, parallel resonance occurs when the supply frequency creates zero phase difference between the supply voltage and current producing a resistive circuit. Okay, this is the example, the circuit diagram that we do. Okay, as you can see, a parallel resonance circuit consisting of a resistor 60 ohm and inductor 200 millihenry and capacitor is 120 microfarad. And we use is connected across a sinusoidal supply voltage with a constant output of 100 volts at all frequency. Okay, next, as you can see here is how to calculate the frequency, resonance frequency. Okay, so for the resonance frequency, we use the formula 1 over 2 pi square root LC, inductor and capacitor. Okay, for this, as you know, the inductor is 200 millihenry and the capacitor is 120 microfarad. So when we calculate, we got 32.5 Hz for the resonance frequency. Okay, next, as you know, the resonance will occur when the XL equal to XC. So as you can see here, for the formula XL is 2 pi SL, 2 pi frequency inductance. So when we calculate it, the resistance is 40.8 ohm. And for the LC, is 1 over 2 pi SC, C for the capacitor. When we calculate, we got the same. So XL equal to XC, 40.8 ohm at the same frequency, 32.5 Hz. The next, quality factor. Okay, quality factor, we use the formula R over XL or R over XC, is the same, right? Because XL equal to XC. So we take SL as an example. So R over 2 pi SL. So 60 over 40.8. We got the quality factor is 1.47. Quality factor used is to find the current in the resonance. Current magnification, IMAX. And for to find bandwidth. Okay, next. Bandwidth. Bandwidth is the frequency between frequency high and frequency low. So how to find bandwidth is a formula resonance frequency divided by the quality factor as before. So 32.5 the resonance frequency divided by the quality factor 1.47, we got 22 Hz the bandwidth. So how to find the frequency low and frequency high. So frequency, resonance frequency minus 1 over 2 bandwidth. Then we got 21.5 Hz for the lowest frequency. And for the highest frequency, resonance frequency plus 1 over 2 bandwidth, we got 43.5 Hz. So 43.5 minus by minus the 21.5 Hz, we got 22 Hz for the bandwidth. So next, current in a parallel resonance. Okay, at resonance, the dynamic impedance of the circuit is equal to R. So we use IT equal to IR. So how do we calculate the IR? IR equal to V over R, right? Okay, 100 over 60 ohm for the resistance. 100 is the VS, voltage source. 100 volts minus divide 60 ohm, we got 1.67 amp for the IC or IR. Okay. For the IMAX, current magnification equal to Q over Q times IT. So Q we got from the quality factor, IT from here. So we got 1.47 times 1.67, we got 2.45 amp for the IMAX, current magnification. Okay, next. Okay. Note that the current drawn from the supply at resonance, so the resistive current is only 1.67 amp, while the current flowing, okay, this 1.67 amp, while the current flowing around the LC tank circuit is larger at 2.45 amp. We can check the value by calculating the current flowing through the inductor or capacitor at resonance. So at the resonance, the current through the inductor and the capacitor. Okay, first we can see the current through the inductor. So how to calculate it? We use V over SL, or we can expand it to V over 2 pi SL, the inductance. So in the value, 52.5 Hz, 200 millihenry for the inductance, and we got 2.45 amp. Okay, it's the same for the capacitor, but it's different from here because it's for the capacitor, right? So V, oh, I forgot to divide here. So V divide XC, V over XC equal to V over 1, V over 1 over 2 pi FC. So V is the XC, 1 over 2 pi FC. So V divided by, okay, 100 for the volt divided by 1 over 2 pi FC, the frequency 32.5 Hz, and for the capacitance 120 microfarad. So when we calculate it, we got also the same 2.45 amp. Okay, this is the resonance, the current flowing at the resonance. Okay, thank you.
Okay, today I will talk about the discussion. The measurement value that we get from the simulation is IT 1.667 ampere, IR 1.667 ampere, IL 2.441 ampere, and IC 2.458 ampere. While in manual calculation we get 1.67 ampere for IT, 1.67 ampere for IR, 2.45 ampere for IL, and lastly 2.45 ampere for IC. So we can say that the measurement value and the manual calculation value is slightly the same. Next, why the value IL and IC is same? First, this is because at resonance there will be a large circulating current between the inductor and the capacitor due to the energy of oscillation. Then, parallel circuit produce current resonance. Second, the current flowing through the circuit must also be at its minimum as the inductive and capacitive branch current are equal. IL equal to IC and 180 degree out of phase.
So guys, the conclusion of parallel resonance circuit is the circuit impedance is purely resistive because there is no frequent term present in it. If the value of inductance, capacitance and resistance is in Henry, farads and ohm, then the value of circuit impedance will be in ohms. The second conclusion that we can conclude from this chapter is the value of impedance will be very high because of the ratio L per C is very large at parallel resonance. As we can see on the table shown on parallel resonance circuit is impedance at resonance is in maximum. The third conclusion that we can conclude from this chapter is the value of circuit current IR equal to V per impedance is very small because the value of impedance is very high. And the last one is the current flowing through the capacitor and the coil is much more greater than the line current because the impedance of each branch is quite lower than that of circuit impedance. Okay, thank you.